Good afternoon, everyone. Thanks for coming out. I know it's kind of a really dreary Monday, and it's kind of a long walk over here from JT, so I appreciate you guys coming out. So, like Dr. Haugen said, I'm going to talk to you a little bit about what I was doing this summer, what my work involved, and what the project I was contributing to were. So just an overview, I'm going to give you a little introduction to myself, some background on the project I was working on, the contributions I was able to make to that project, what the results were, the conclusions that we had, and I'll have some time for questions at the end. So just a little bit about myself. I'm fourth year engineering, physics, and society. I was a research associate at NASA's Goddard Space Flight Center in Greenbelt, Maryland this past summer, and I was working in the astroparticle physics laboratory while I was there. So the mission I was working on was the Advanced Energetic Pair Telescope. So this is a telescope that's being developed to do medium energy gamma ray polarimetry. So polarimetry meaning that this telescope is going to be able to measure the polarization of photons which are incident on the detector. And the medium energy gamma range is considered to be between 5 megaelectron volts and 200 megaelectron volts. So megaelectron volts and electron volts are a unit of energy, something I'm going to be referring to quite a bit today because that's tended to be the unit of choice for NASA when they're talking about gamma ray telescopes. So this energy region is really interesting. There hasn't been a mission developed by NASA yet that has specifically been optimized for detection in this range. So my supervisor this summer saw a gap in our understanding of events that are happening in this region. So things like the extragalactic diffuse emission, which are gamma rays coming from everywhere in the universe. We don't really have a great understanding of the gamma rays in this range from that source. Also supernova remnants, pulsars. There's a whole long list of sources I could go through, but there's a lot of science that can be done in this regime. And if you look at papers right now that are trying to analyze data in this region from other telescopes which are optimized for high energy gamma rays or high energy X-rays or low energy gamma rays, they have about 20 to 30% error depending on the paper you look at. So that's not really that great, and my supervisor is really hoping that if this satellite launches, it will help better our understanding of that range. So as I mentioned, it's doing polarimetry, so it's measuring the polarization of waves, and the instrument that does this is called a polarimeter. So it has a lot of advanced technology. I'm going to explain that in a couple of slides, but it allows us to get close to an angular resolution allowable by the kinematic limit. So if you think about the diffraction limit of optical telescopes, that tells you how close 2 points can be in the sky and you can still resolve them separately. That's a similar kind of thing for gamma ray imaging is the kinematic limit, so that's a good thing to think about, that this technology has been developed and pushed through so many iterations that it can get down to this limit now. And it really works by detecting pair production events. So I'm going to explain just a little bit about what pair production is. So pair production is one of the mechanisms through which photons interact with matter. The other interaction mechanisms being the photoelectric effect and Compton scattering. So this happens when you have a gamma ray which will interact with matter and produce an electron and its antiparticle, a positron. So that's demonstrated by this diagram, which isn't entirely correct. It's a little bit of a simplified version of it. But essentially what you're getting is a gamma ray coming in and an electron and a positron coming off. And the minimum energy that's required for this is 1.022 megaelectron volts. That's twice the rest mass energy of an electron, if you're curious. And that kind of tells you why our energy range starts at 5 megaelectron volts, because we're detecting pair production events, so we need pair production to be happening. So this is what the detector looks like. It's a gas volume filled with 1.5 atmospheres of a mixture of argon and CS2 gas, 95% argon and 5% CS2. So the argon has been chosen because it has a relatively large cross-section for pair production events, so meaning that pair production events are pretty favorable in this gas. And then the CS2 is an electronegative particle which will kind of grab onto those electrons that are generated throughout the volume and carry them down to the detector at the bottom. So as these gamma rays come into the gas volume, they're going to interact and create an electron and a positron. And as those electrons and positrons travel through the gas volume, you're going to get these ionization tracks that you see here. There's then a field-shaping cage which is wrapped around the gas volume, and it's biased to about 1 kilovolt per centimeter. That's what we're hoping for the finalized detector. And that's just going to accelerate all of the freed electrons down towards the microwell detector, which is this thing that we see down here. So the microwell detector will further provide an avalanche effect for the electrons which hit the well, and it gives you a gain of about 10 to the power of 4, so 10,000 times the signal that you would get from a single electron being generated. And what's really neat about this detector, it's something that I found really interesting and really clever, is that they track the time that each event hits the microwell detector. So each signal that it sees, it'll track the time, and then when you put all these back, it'll take that time data and give you a Z projection of the path as well. So by having your spatial tracks, figuring out where they are on this plane, plus the time that it comes in, you're able to reconstruct a three-dimensional image of the path that was coming from your electron and positron. And then by back propagating those, you can figure out where your gamma ray was coming from. So you can figure out what source is it coming from, and then you can determine the energy that it's coming from, and you can learn a little bit more about the source that you were pointing at. So when I showed up to NASA, this is the point that we were at. We knew that the mission had great angular resolution, and it was going to provide a lot of new science, and nobody had really done this range before. So it was something really interesting, something new that could be tackled. However, you're sending a pressurized chamber into space, which is something that NASA and most space agencies wisely choose to ignore because you're in a vacuum and you're sending up a small contained pressurized gas. It's kind of a bad recipe if something goes wrong. And the microwell detector technology has never been used before in space. So there's a little bit of hesitation in launching something that we don't know whether or not it's going to work. So what we needed was a way to prove this technology before NASA was willing to invest about $500 million or more into launching this satellite. And that's where they came up with the AdEPT Pathfinder CubeSat. So a CubeSat is just a small satellite platform, and I'll explain a little bit about that in a slide, but it's a great chance to prove the technology for low cost. But we had some questions to answer first, like, would a smaller detector work? So to give you a sense of scale, these satellites are roughly 3 liters in volume normally. The entire AdEPT mission, the original concept was planned to be 8 cubic meters. So that is an order of magnitude larger than what you would get from this satellite. So we weren't sure if we had this smaller detector, is it even going to work? It's a smaller detector, smaller detecting volume, you may not get events that are detected. And with that being said, what is the smallest we could go? Do we have to go to a 3U? Could it be a larger satellite, or could we go even smaller? And would the low Earth orbit environment be okay? So when you're in low Earth orbit, that's tending to be around 400 to 800 kilometers in orbit around Earth, but you still get some of the effects of the magnetic field, some atmospheric effects, so would that environment be all right? And how would it behave in this radiation environment? So being in space is a much more volatile environment than here on Earth. We have the atmosphere to protect us. So you're going to have electromagnetic radiation flying around, you'll have beta radiation, protons, galactic cosmic rays, a whole plethora of stuff that you have to consider. And this is the big question, would we be able to get any useful scientific data out of it? If we can take this small version of the satellite and show that we're launching this and we're still getting science out of it, it boasts very well for a full-size satellite mission. So just a little bit about CubeSats. So I'll be mentioning U's during this presentation, which is a standard CubeSat unit, which just means a 10 centimeter by 10 centimeter by 10 centimeter cube. You can see here, these are some of the different sizes of them. So the picture I just showed was a 3U satellite. These are typically used when you want to do a prototyping mission or for universities or agencies that don't have large budgets, but it's a great chance to prove a technology because it has a much lower cost than a full-scale mission. So this is what I was asked to do this summer. I wanted to develop a simulation of the Pathfinder CubeSat in low Earth orbit, determine how this smaller instrument is going to interact with different types of radiation, and like I said earlier, the main question, will we be able to get any scientific data out of this? So in order to answer these questions, I decided to create a simulation. So I was using C++ and the JAWNT 4 Monte Carlo toolkit. So this toolkit just gives you a way to model radiation interactions with different types of matter. It allows you to specify the detector geometries that you have. So I was able to create the satellite itself and figure out how that would work and all of the different materials that are included, because radiation behaves differently when it interacts with different types of material. And you're also able to specify what types of interactions are allowable, which will help you determine the computation time. If I allowed every single possible type of interaction to happen, these simulations probably would have taken a couple days to run, but I got it down to just taking a day to run, so that was pretty happy. And yeah, you're allowed to specify which volumes are detectors. So you can choose where you care about interactions happening, which again just helps with computation time. And in order to do this, I had to make some simplifications and assumptions about the radiation environment and about the satellite itself. The biggest one that we had to make was that we only considered the detector of the satellite. We didn't worry about the rest of the satellite below it, because although you can say to JAWNT, I care more about the detector, it's still going to have to figure out what's happening in that block of aluminum that's below you. So we chose to ignore that just because it would take way too long to calculate all of those. We ignored certain parts of the detector, of the instrument. So bolts and seals and everything. They're essentially made out of the same materials as the satellite, so we figured we could ignore those. And we also assumed that the detector was efficient, 100% efficient for any event that deposited more than 100 electron volts in the gas volume. So if we had some form of radiation come in and it interacted with some form of matter in this satellite, if it was greater than 100 electron volts, we assumed that the detector would be able to see this. And we also assumed an isotropic radiation environment. Now this isn't entirely true in space, but in order to figure out how the whole detector behaved, we decided to go with this selection. So that means that if I took my detector and I got this sphere of radiation and put it around my detector, I would have radiation coming from every single point on the sphere. And I have here that it followed a cosine angular distribution. That just means that it can come off at any point and at any angle. So we're testing as much of the detector as we can. We're trying to avoid any type of bias based on geometries that we could. And we also use monoenergetic sources, which again isn't exactly what you see in space, but this allows us to figure out the instrument's behavior over a wide range of energies. So this is the detector that I made. Sorry, the contrast isn't too great, but I'll try and explain what's going on here. So this is what I wrote in JAWNT 4 and then visualized it with a plugin called Qt4. Making this little square took about 800 lines of code. And so what you see here, this darker outline is the pressure vessel. So that's an aluminum capsule that is holding in everything. It's holding in the gas, and you probably noticed that it's pretty thin, and that's because at its thickest, which is this part here, ignoring the larger cutouts, that's only 2 millimeters thick of aluminum. So I wasn't responsible for the mechanical, thankfully, so I've just been told it would work, so I was okay with that. The PCBs are everything that are housing the electronics, so those are made out of a material called G10, which is a common PCB material. It's silicon-based. The sensitive gas volume is the argon CS2 gas that we had. So it doesn't really show up, but the area between these two PCBs is what we considered the sensitive detector. So any event that happened in this region, we assume that the field shaping cage is going to accelerate these electrons down to the detector and they will be detectable. Because in order to program an actual field shaping cage and have it accelerate electrons, again, it would increase computation times and probably take a lot more lines that I really didn't know how to code. The rest of the gas volume was filled with the same argon CS2, and this little yellow piece that you see there is the silicon microwell detector that we had, so it's just a slab of silicon that was there. So within JAWNT, we use the G4 multifunctional detector. There's a bunch of different ways in JAWNT to figure out what type of interactions are happening and how you track these events. The G4 multifunctional detector is great because, as its name suggests, it can track a bunch of different things being multifunctional. So with this, we're able to look at the generation of secondary particles, so electrons, positrons, and gamma rays. Since we're looking for pair production, seeing that signature of an electron and a positron at the same time is really what I was trying to find out with this simulation. And something that was of interest to my supervisor is how much energy is deposited by these particles in the gas volume, and what about the secondary particles? How much energy do they deposit? So there was a lot of things that were being tracked with every single interaction that was happening. And just to give you a sense of scale, one energy range that I would simulate would consist of about 1 billion photons being simulated, anywhere between 100 million to 1 billion, depending on the environment. So I was doing that for 1 MeV up to 10 MeV spaced logarithmically, and then 10 to 100 and 100 to 1,000 MeV. So you can get an idea of why these simulations took so long to run, but there's something that had to be done. And then all of this information for every interaction that happens is put into a CSV file. My computer is now still full of these CSV files. There's about 150 files that I had to make to get the full energy range figured out. And we use those to do later processing and figure out what's the sensitivity of this instrument. But one thing that we had to determine was how big is this detector going to be. So I talked earlier about CubeSat sizes, and we came up that either a 1U instrument or a 4U instrument, so a 3U satellite or a 6U satellite, those are going to be the two ways to go. So we did a trade study and tried to figure out what's the best possible way to build this satellite. Excuse me. So you can see here, there's just some sizes. So the 1U satellite is 100 millimeters by 100 by 112.5, whereas the 4U instrument gives you about 5 times more volume. I know that sounds like I did my math wrong, because 1U to 4U multiplied by 4, it should be that simple. I thought it would be too, but it turns out when you start looking at the internals of this detector, there starts to be a little bit more room that you can play with when you get to a 4U size. So you don't have to make the walls 4 times as thick, they can just be a little bit thicker. The detectors can be spaced just as close together, you don't have to quadruple that room between them. So you end up getting a much larger detecting volume, and we determined that although it is more expensive to build a 6U satellite, essentially it's twice the size, and there's not as much experience building 6U satellites, and that's just globally because they're still a relatively new platform. Most people have tended to go towards 3U satellites. We still decided that that would be the best choice for this project because it has that much larger detecting volume. So once we decided on that, my supervisor asked me to CAD up a detector and show him what it would look like. So thankfully they had a 1U instrument and I was able to base this off of that, but this just shows you some of the things that I had to exclude from the simulation. So these wires that were in there along the field shaping cage, I ignored those because they tend to be really small and don't have a high chance of interacting. All of this cross-hatching in the pressure vessel, that was ignored because it would take way too long to program those in, and all of these bolt holes and stuff were just assumed to be one solid piece. So at this point, I had the simulation running, I knew what the instrument was going to look like, and I had a bunch of files figured out, but I had to figure out essentially what is the detector sensitivity, how many events is it going to detect per orbit, and getting back to that main question, will we get any useful science out of it? So we did this through a calculation of what's called the geometry factor. So this number has really weird units of centimeters squared steradians. So I'll try and explain that in a simple way. So it's essentially the effective area of your instrument, what part of your instrument is going to be able to detect interactions, while still considering the size of your instrument and the size of your source on the sky, or considering a sphere that's surrounding you. And just to explain this equation, so ND is the number of detected particles, so how many interactions are within that volume that are considered detectable, over the number of simulated particles, and multiplied by this 4 pi squared factor. That comes from the geometry of the source itself, and then r squared comes from the radius of the source around it. So like I mentioned before, we took our instrument and you place a sphere around it. The radius of that sphere is the r squared that's in there. So I ended up having to write a Python script. First year programming eventually came back to help me out. And this is the data processing algorithm that we came up with, extremely simplified. So it would take in these CSV files that we had, and it would first do a check if there was at least 100 electron volts deposited in the volume. If not, it would just skip over that event and start considering the next one. If there was, it would say, okay, did we create secondary particles that were electrons and positrons? And if it did, it would say, great, so we can add our ND factor to the geometry factor. We'll add 1 to that and then consider the next event. If not, what was that event? So we looked, were there any particles generated at all? Or was it just something depositing all of its energy? Was it a Compton event? Was it a photoelectric event? So we tried to look at what was really happening inside of this detector. And this is the graph that I ended up coming up with. So this is the geometry factor as a function of incident photon energy. And now if you've studied photon interactions with matter, you may notice that this shape is very similar to the cross-section of pair production in any medium. So that was a really encouraging result because we saw that as the energy increases, the geometry factor will increase and then eventually plateau at a certain volume or value. So yeah, that whole factor that I showed before, the ND over NR factor, went into making this graph here. And then in order to figure out how many counts we were going to get, we had to consider different sources on the sky. So for gamma rays, we considered the Crab Nebula, which is a very bright medium energy gamma ray emitting source on the night sky. The galactic core, which if you go to somewhere really, really dark at night and you see that band across the sky of the Milky Way, that band is emitting a lot of gamma rays, so we looked at that source as well. And the extragalactic diffuse, pardon my misnomer there, I called it the galactic diffuse, but this is just all of the radiation that's coming from outside of our galaxy that's constantly flying around. And this is just a map by the Fermi telescope in the gamma ray. I just wanted to show what some of those sources would be. So the galactic center is this band, that really bright band that you see there. The Crab Nebula is that bright dot over there. And then the extragalactic diffuse is all of that blue stuff. So you can see it's a pretty isotropic source just coming from all the way around you. And this is the type of map that we were thinking we could make with the AdEPT Pathfinder CubeSat. Probably not the same level of resolution, but it would be a great way to prove that this technology works. So when you take those spectra and you multiply them by the geometry factor, you end up getting these graphs, which is your differential count rate. So photons per second per MeV. And you can see that the higher spectra that we have are giving the higher count rates. And they tend to follow the shapes as you would expect, just a multiplication between the two. And then if you take the integral over all energies, you can end up with the integral count rate. So the way to read this graph, it confused me for a while this summer, but it says if we're at this source right here, so we're at 10 mega electron volts, for 10 mega electron volts and all higher energies, we will get this count rate, which is around 2 times 10 to the minus 3 counts per second. So that's how many photons it will detect per second, or how many gamma rays it will detect. And these are the numbers that I ended up coming up with. So the orbital duty cycle on these graphs, or on these numbers here, just say for how much of my orbit can I see it. So the extragalactic diffuse, like I said, it's always around you. So no matter where you are in your orbit, you're going to be getting hit by that. The Crab Nebula is a very small spot on the night sky, so for half of your orbit, it's blocked out by the Earth, and then for the other half, you can see it. And the galactic center, it's a very wide band, but again, Earth can block that out from you, so you only see it for about 65% of your orbit. So we ended up with 6.5 counts for the extragalactic diffuse, just shy of 2 counts for Crab and 12 counts for the galactic center, which gave about 20.5 counts per orbit. And then we also had to consider different noise sources in the night sky. So protons are constantly flying around. They're very heavy particles. They like to interact with things. And it turns out that they really like to interact with our detector as well. So you can see here, these count rates sadly are many orders of magnitude higher than what we had for the gamma rays, but my job was just to design the simulation, not really come up with solutions for that, but we did discuss some different ways to try and get rid of that. And these are just based on different orbits. So all of this data was taken from the European Space Agency. They have simulations which kind of tell you, if I'm in this orbit, you can expect to see these many counts. And again, this is just the integral count rate. So for how many, above a certain energy, how many proton counts am I going to get in the instrument? And then we did the same thing for electrons. And you can see a much stronger orbital dependence here. So if you're in an equatorial orbit, there's a very low flux of electrons coming through, so you don't really have to worry about those all that much. But they're still a significant source that has to be considered. And these events are just going to be picked up as noise in the detector. So if something hits the microwell detector, it's going to take an image and try and figure out what happened. So there is some interesting onboard processing which is going to be happening where it'll be able to do image rejection before transmitting data down. Because you can see with these count rates and the refresh time of the instrument, I don't want to mess this up, but it was taking images every 50 milliseconds, I believe. So it's generating a whole heap of data all the time, and transmitting down that much data just wasn't feasible for this satellite. So that's another project for another time, but it's definitely going to be interesting to see that being done. And what was really interesting about these is that there was a chance for false positives to be registered by the instrument. So if you have charged particles interacting with a metal, there's a chance that that interaction will kick off high energy gamma rays. And then these gamma rays may go into your detector volume and cause a pair production event, which the detector will say, oh good, we just got a pair production event. So that was something that I wasn't really expecting to see, but it was really interesting that it actually happened. However, there was not a lot of these events happening. It was maybe 1 per orbit, but there was a lot of error on those values just because they're highly unlikely. So what did I end up doing this summer? What were the conclusions that I was able to contribute? We found that there's going to be a lot of noise. You can see that from the last 2 graphs that I showed. So this onboard processing is going to have to be able to filter through the data quickly and extremely efficiently. But one of the possible solutions we came up with is there's something called the South Atlantic anomaly, which is an area over South America where the magnetic field of Earth dips down, and it allows a high flux of particles to get through at that area. So it causes there to be less shielding from charged particles at that one specific spot on the Earth. So what some satellites have done in the past is they actually shut off their instrument passing through that area just because the flux gets so high that their imaging software can't really deal with it. So that's something that we could also do for this satellite. We decided that a 6U satellite with a 4U instrument is the ideal platform for demonstrating this instrument because it has that 5 times larger volume. So we found out that actually strongly correlates to almost a 5 times higher detection rate. And based on those last graphs I also showed you, we determined that an orbit with as low inclination as possible, ideally equatorial, but they don't really launch those for CubeSat, so it's really going to be dependent on what's available at the time. And an altitude between 400 and 600 kilometers seemed to work best for our needs. And this is what my supervisor was extremely happy that I was able to tell him, is that this CubeSat will be able to not only prove that this technology works, but that 20 counts per orbit that we're going to get, that will be able to do some significant science and we'll be able to get something out of this instrument, even though it's such a small instrument. So that's all I have for today. Thank you very much for listening, and I have some time for questions if you guys have any.